So for our last video for chapter 10, we're going to look at phylogenetic trees. They're also called cladograms. So we've been looking at how we can look at the evolutionary relationships between organisms by both dating them to see how old they are and also looking at structural and molecular similarities and differences to figure out what is related. Phylogenetic trees are a different way that we can represent these relationships. So once we've got all the evidence from our fossils and our structure analysis, etc., we can put them into phylogenetic trees. And these are a really simple way to show the relationships between organisms and to see older ancestors versus more recent ancestors. So this is what a phylogenetic tree looks like. It's basically a diagram that shows relatedness between species and allows us to visualize relationships. So there's a couple of key things that you need to note here. There's something called the root. So the root is the point of the line of origin or the divergence point, and this represents an ancestor. So you can see here this root is the earliest common ancestor. So this is the very first animal that diverged into all of the species that you're going to see at the end of the phylogenetic tree. All other points of origin are then called nodes, but these again represent common ancestors. So for instance, the common ancestor between taxon X and Y is this animal here. So this animal underwent a speciation event and it has been speciated into these two different types of species. And then this one, for instance, speciated into, again, two different types of species, and etc. So those roots and nodes represent a divergence point. So that is where one animal has speciated into two different species. We also have our branches. So these branches represent a species of some description. And then we have our leaves. So the leaves is the very end of the branch. So these leaves all represent present day species. So if something is at the end of this leaf, so taxon X, Y, and Z, they are all species that currently exist. So you can see for taxon Z, for instance, this species must be a very old species because its most recent common ancestor is all the way back at the root here. So you can assume from this phylogenetic tree that taxon Z would be the oldest living species, and then taxon X and Y would be the youngest evolving species because their recent ancestor happened a lot later in time. So these are the key parts of a phylogenetic tree. So they can be read backwards to determine close relationships. So you can actually read them this way. So you can start with all of the animals that we know and that exist today, and then you can look back at the nodes that they share and trace them back. So for instance, at this node here, there must be a common ancestor that diverged and speciated into both crocodiles and birds. Another one similarly here, one that we're probably quite familiar with, there was a common ancestor here that eventually diverged into humans and into monkeys. So the closer they are to the right-hand side or to these leaves, the more recent they are. The more towards the left, the older they are. So this node here represents the oldest common ancestor for all of the species in this tree. And we can keep traveling back in time. So for instance, the fish in this scenario would be the oldest living species because its ancestor was right back at the start of this and it hasn't evolved since. The second most oldest species would be our amphibians, which trace back to this node here. This node here is tracing back to our snakes and lizards and our marsupials. And then the closer we get to those end leaves, the more recent those species are. So you will have to both read a phylogenetic tree, and you'll also be able to have to look at some data and be able to figure out how to construct a phylogenetic tree as well. So for instance here, we've got this data here that's looking at two different traits. So we're looking at having fur and having forelegs. So you can see that the bony fish has neither of those things. The amphibian has one of those things, and both the marsupials and the placental mammals have both of those things. So you can assume that the animal that doesn't have either of these traits is going to be the animal that is the oldest common ancestor for the more evolved animals. So if we were to construct a phylogenetic tree here, we would have obviously the starting convergent point, which we don't know what the common ancestor is, and then our first offshoot would be our bony fish, and they wouldn't have any divergent points from that. Then we would go off and we would diverge our amphibians who have 4 legs but no fur. And then by the end of it, we'll have 2 equal nodes here for our mammals and our marsupials. So it's really just about finding the divergent points between species, and we can often do this by seeing who has the most complex traits and who hasn't evolved those complex traits for a very long time. So there's a couple of points in a phylogenetic tree that might look a little bit strange. So since fossil dating isn't always completely accurate, like we know, if we're using relative dating, for instance, we're not exactly sure about a certain age, so we can sometimes be a bit uncertain about relationships. So you'll see that there is a lack of a node between Y and Z. So here we have not connected this with a node. And what that basically means is that we don't really know what the common ancestor or the point of divergence was for these two species. So we're not exactly sure when Y and Z speciated, and we're not really exactly sure what species it was from either. So we can leave a little gap there to represent that. The break between W and X, so you can see that there's a little break here, means W is possibly an ancestor of X, but there is no evidence. So we can use a little gap here to say, hey, look, we think that X has evolved from W, but we don't have sufficient evidence yet, so we can represent that by a little gap there. The branch for species S does not reach the end of the tree, which means it is extinct. So remember that all of the animals that, or organisms that are on the leaves, the end leaves of the diagram, they're present day animals. So if there is a species that does not reach those leaves at the end, we can assume that that species is extinct. And if adaptive radiation occurs, which is basically speciation that happens really close together, so we're not exactly sure what came from what, we can have several different branches coming out of one node. So for instance, we've got T, U, and V. We're not exactly sure which one came first or which one diverged from what. So we just kind of use one node to represent all of those species. So you need to be able to read these trees to determine relationships between species and find common ancestors, recent ancestors, and older ancestors as well. So hopefully this helps, and if you have any questions, bring them to class and I will see you there.